Welcome to the Altera learning course, eCPRI Intel FPGA IP, Architecture and Interfaces. This training is the second in a series of courses designed to help you become familiar with the IP solution targeting the Enhanced Common Public Radio Interface, or eCPRI protocol. By the end of this course, you will be able to describe the architecture and functional blocks that make up the eCPRI IP. From there, you will learn how packets are routed and processed by the IP. Finally, you will learn about the interfaces found on the IP that you will use to connect your transport and application layer logic. In this training, we will start with a look at the IP's functional blocks. Then we will study the incoming and outgoing packet flows and how they are handled by the IP. In the last section, we will study the various interfaces on the IP for connection. This training assumes that you have a good understanding of the eCPRI protocol, as we will not spend much time defining its details. The course also assumes you are familiar with the Quartus Prime Pro software tool suite and its design flow when targeting Altera FPGAs. And while not absolutely necessary, a good understanding of Altera FPGA architecture is helpful. If you have further questions on the 3GPP or eCPRI spec, here are links to some resources. This includes links to the eCPRI IP user guide and the design example user guide. If you need to download and license the eCPRI IP, you can find information on this in the IP user guide. So we start with a look at the eCPRI IP functional blocks. This diagram displays the main functional blocks found in the eCPRI IP. Let's take a deeper look at these blocks. Starting from the FPGA fabric side, highlighted in the dotted box now, is the eCPRI IWF Type 0 block. Like we learned in the Getting Starting training, it is there to bridge between the eCPRI IP protocol and the eCPRI IP logic behind it. So it is only instantiated in the IP when IWF Type 0 support is enabled. To its right, you can see the interfaces available for connecting to the eCPRI MAC. Highlighted now is the core of the eCPRI transmit and receive logic. In the transmit path near the bottom, moving from the FPGA fabric to the left, you can see the header mapper and concatenation blocks. The header mapper appends the eCPRI common header to the outgoing message received from the fabric. The concatenation block can then concatenate multiple of these eCPRI messages into a single Ethernet frame or an IP UDP packet. Sideband signals are provided to signal concatenation. In the receive path along the top, moving from the IP core into the FPGA fabric on the right, you can see deconcatenation and header mapper blocks. The header deconcatenation block returns concatenated messages back to their original eCPRI messages. The header demapper block removes the eCPRI header from the incoming message and forwards it into the FPGA logic. The CSR block at the bottom contains and provides access to all of the configuration registers for the IP core. The special eCPRI message 5 parser block is used to initiate one-way delay measurement calculations. It is used to remove the transport delay from the transmitting side to the receiving side. We will talk more about this later in the presentation. Next is the Ethernet frame section. For outgoing eCPRI messages on the transmit path, the Ethernet header insertion block adds Ethernet headers to eCPRI messages. It can optionally add IPv4 UDP headers to the packet according to how the IP core is configured. For incoming eCPRI messages on the receive path, the Ethernet header removal block removes Ethernet headers from the eCPRI messages. It can optionally remove IPv4 UDP headers as well. The final section is the L2-L3 parser section. Within this section are the packet classifier and the packet queue. For the transmit path, the packet queue stages the incoming Ethernet frames coming from the external streaming sync interface and performs arbitration between them and eCPRI packets coming from the core. For the receive path, the packet classifier accepts Ethernet frames from the MAC and detects the packet format. From there, the packet classifier routes packets to either the eCPRI IP interface or the external streaming source interface. We will talk more about the operation of these blocks and their interfaces in an upcoming slide. Now that you are familiar with the blocks inside the IP core, let's look at the interfaces and how messages and packets flow through the core. In this section, we will start with the packet interfaces to the IP and then look at how packets are prioritized during routing. We then will take a quick look at the CSR interface and the IP's required clocks and resets. We will end with some additional interfaces of which you should be aware. The eCPRI IP has two sets of avalanche streaming source and sync interfaces for sending and receiving packets. The eCPRI IP source and sync interfaces are for sending and receiving eCPRI message packets. The one external streaming source and two sync interfaces are for sending or receiving eCPRI, C and M plane and synchronization packets, as well as any other type of frame packet such as Ethernet or IPv4. This slide demonstrates how general eCPRI message packets flow through the IP core using the numbered arrows. 1. You have an eCPRI message packet coming in from the FPGA. The header mapper appends the common header to it. Concatenation may also take place based on a user-controlled signal in the sync interface. 2. The Ethernet header insertion block inserts the Ethernet header and forwards the packet to the MAC. 3. On the receive side, the Ethernet packet containing an eCPRI message passes through the packet classifier. The Ethernet header is removed by the Ethernet header removal block. 4. Deconcatenation is performed, if needed. The eCPRI header removes the common header, and then the final payload is forwarded to the user or FPGA. Note that if the IWF type 0 block is enabled, then the packets originate as CPRI frames in the core logic and are converted to eCPRI messages. Responses are converted back to CPRI frames. This slide highlights the PTP synchronization and C&M, or control, and management flow again using the numbered arrows. 1. The PTP and C&M packet are presented to the IP through the external streaming sync interface. Remember, this is also the interface used for other non-eCPRI message packets. The packet is then presented directly to the packet queue. 2. The IP forwards the packet to the MAC interface for transmission. 3. On the receive side, the packet classifier block parses the packet, detects that it is either a non-eCPRI packet or it is an eCPRI packet with a non-matching MAC address or user-configurable VLAN ID, and routes it to the external streaming source interface. When either the external streaming source or sync interface are used, no additional processing is performed by the IP core, so all transmit and receive processing of the packets must be performed by user-defined fabric logic. This diagram highlights how arbitration works. 1. A PTP or C&M packet comes in. 2. At the same time, we have an eCPRI packet coming in through packet transmission. This results in a collision between the packets. 3. Priority arbitration determines the order in which packets are sent, using the configuration priority order set by the user. The CSR interface is a memory-mapped interface used to access the IP's internal register map for reading and controlling IP configuration settings and features. Using the CSR interface, you can program MAC, VLAN, IPv4 and UDP addresses to be used for packet filtering and routing. Issue eCPRI message 5 packets. Lastly, read, write, clear, and mask eCPRI errors. Use the link on this page to view the complete IP register map. This slide shows an example of using the CSR interface to perform the eCPRI one-way delay measurement on the transport link. This flow requires the Ethernet IP's PTP hardware to work. So, if the Ethernet MAC is selected without the PTP option, or if using another vendor's Ethernet MAC without PTP, then this feature will be disabled or not supported. This measurement can be performed with, or without, a follow-up message. Looking at the flow in the diagram, 1. You write to the eCPRI message 5 control register. 2. The IP then issues a message 5 request packet to the MAC for transmission, adding to it a timestamp value taken from the time of day management block. 3. The message 5 response packet with timestamp and compensation value from the PTP are received, and from this the transport delay is determined. The eCPRI IP CSR space contains many registers for monitoring and handling IP and transmission error conditions. For example, there are registers that flag for situations like buffer overflows, ECC errors, packet errors, and timeout errors. These registers are all documented in the eCPRI user guide cited earlier in this presentation. There, you will find the error conditions checked, the register and bit locations used for logging, how the IP behaves when these errors occur, and the recommended response from your system. This table provides some examples of error conditions and recommended mitigations from your logic. Feel free to pause the slide and look through the table. As mentioned in the last slide, these error conditions can be found in the user guide. For clocking, the clock TX and clock RX signals on the IP core must be driven with either 156.25 MHz or 390.625 MHz clocks, depending on the Ethernet version. The configuration interface clock CSR, must be connected to a 100 to 162 MHz source. The external streaming interface runs off the external sync clock signal, which must be clock TX. The MAC clocks MAC clock TX and MAC clock RX are driven by clocks generated by the transmit and receive interface clocks from the Ethernet IP. For resets, the reset TXN and reset RXN IP signals are inputs to the eCPRI IP from the Ethernet MAC. The reset CSRN signal is an input that resets the IP control and status registers. Again, please see the user guide for the complete list of IP clock and reset signals. Finally, we want to highlight a few other interfaces found on the IP core. There are the Ethernet interfaces to connect to the Ethernet MAC. These include the PTP and TOD interfaces. The ORAN interface signals TX transport CU and RX transport CU appear when ORAN IP pairing is enabled. Lastly, when IWF Type 0 is enabled, then additional interfaces appear for connecting to eCPRI logic. These include the IWF interfaces and the eCPRI MAC interfaces. This concludes our look at the architecture and interfaces of the eCPRI IP. In this training, you learned how the blocks in the eCPRI IP work to process eCPRI and other packets in a system. This will help you devise the best plan for employing the IP in your own fronthaul application. You also learned the interfaces found on the IP core that you use to connect your own transport and application layer logic in the FPGA fabric. The Altera training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We welcome any feedback you may have. Thank you for viewing this course and have a good day.